a balanced three-phase system, the loads on each phase are equal. However, in real-world systems, imbalance is common due to varying loads on different phases. When dealing with imbalance, it's essential to consider the impact on transformers and the overall system. Let's discuss transformer selection for single-phase loads. A delta Y transformer, specifically a 480 volts to 120/208 volts transformer, cannot provide 240 volts directly as its secondary voltage is 208 volts. A delta-delta transformer, stepping down 480 volts to 120/240 volts with a center tap, can provide 240 volts but is heavily derated for 120 volts loads. For example, a 75 kV amps transformer would be required to handle the 120 volts loads, which is oversized and not cost-effective. Here are some strategies for dealing with imbalance. Firstly, consider limiting imbalance at the 480 volts level. You can pull off one leg of the 480 volts service and use a single-phase transformer to step down to 120/240 volts. This approach limits the imbalance to the 120 volts loads while keeping the 480 volt system balanced. Secondly, think about balancing imbalance at lower voltages. You can keep the 480 volt system balanced and use a delta-delta transformer to step down to 120/240 volts. Distribute the 120 volts and 240 volts loads evenly across the three phases to minimize imbalance at the lower voltages. An additional option is using a buck-boost transformer. A buck-boost transformer can be used to adjust the voltage on one phase of a balanced system. This allows for the creation of the 240 volt single-phase supply from a balanced three-phase system. Based on the provided information, the best option might be to pull off one leg of the 480 volt service and use a single-phase transformer to step down to 120/240 volts. This approach limits the imbalance to the 120 volts loads while maintaining a balanced 480 volt system. Some additional considerations. Firstly, calculate the total loads on the 120 volts and 240 volt circuits to determine the appropriate transformer size. Secondly, ensure that the transformer selected meets the load requirements and has adequate capacity for imbalance. Thirdly, monitor the system regularly to ensure that imbalance remains within acceptable limits. When evaluating transformer options, remember that delta Y transformers are generally used for stepping down voltage while providing a neutral connection, but they do not directly provide 240 volts in the 120/240 volts configuration. Delta-delta transformers can provide 120/240 volts through a center tap, but they are susceptible to derating when a significant portion of the load is single-phase, especially at 120 volts. Using a single-phase transformer off one leg of the 480 volts service isolates the single-phase loads and prevents them from directly impacting the balance of the three-phase system. This approach is often preferred when single-phase loads are substantial and require 240 volts. However, the impact on the 480 volt system must be assessed. Calculate the current drawn from each phase of the 480 volt service with the single-phase transformer in operation. Ensure that the resulting current imbalance does not exceed acceptable limits for the source equipment and wiring. If the imbalance is too high, consider redistributing loads or using a different approach. The size of the single-phase transformer depends on the total voltamps of the 120 volts and 240 volts loads it will serve. Add up all the loads, taking into account any diversity factors, and select a transformer with a kilovolt amps rating that exceeds the total load. Consider future expansion when sizing the transformer. Buck-boost transformers offer a different way to address voltage requirements. They can be used to increase or decrease voltage by a small amount, typically a few volts. In this case, they could potentially be used to derive 240 volts from a 208 volt source, but careful consideration must be given to the transformer's volt amps capacity and the voltage requirements of the loads. Remember that buck-boost transformers are typically used for small voltage adjustments and may not be suitable for large single-phase loads. When implementing any solution, ensure that all wiring and equipment comply with the National Electrical Code, or NEC, and any local electrical codes. Proper grounding and overcurrent protection are essential for safety and reliable operation. Consider the use of power quality monitoring equipment to track voltage and current balance over time. This can help identify potential problems early on and prevent equipment damage. When distributing single-phase loads across a three-phase system using a delta-delta transformer, aim for even distribution. This minimizes the impact on the transformer and the overall system balance. However, perfect balance is often difficult to achieve in practice, so it is important to monitor the system and make adjustments as needed. If the 120 volts and 240 volts loads vary significantly over time, consider using a transformer with a high kilovolt amps rating to accommodate the fluctuations. This can help prevent overloading and ensure reliable operation. Evaluate the cost of each option, including the cost of the transformer, wiring, and installation. Also, consider the long-term operating costs, such as energy consumption and maintenance. The most cost-effective solution may not always be the one with the lowest initial cost. If the single-phase loads are critical, consider using a redundant transformer system to provide backup power in case of failure. This can help ensure uninterrupted operation of essential equipment. When selecting a transformer, consider its efficiency. High-efficiency transformers can save energy and reduce operating costs over the long term. Look for transformers that meet or exceed industry standards for energy efficiency. If the pump house is located in an area with frequent power outages, consider installing a generator to provide backup power. This can help prevent damage to equipment and ensure continued operation during outages. Properly label all wiring and equipment to facilitate maintenance and troubleshooting. This can save time and effort when problems arise. Consider the use of surge protection devices to protect sensitive electronic equipment from voltage surges. Surges can damage or destroy equipment and can also cause data loss. Install surge protection devices at the service entrance and at individual equipment locations. Regularly inspect all wiring and equipment for signs of damage or wear. This can help identify potential problems early on and prevent equipment failures. Keep a detailed record of all maintenance and repairs. This can help track the performance of equipment and identify trends that may indicate potential problems. When making changes to the electrical system, always consult with a qualified electrician. A properly installed wiring can be dangerous and can also damage equipment. Consider the use of smart grid technologies to monitor and control the electrical system. Smart grid technologies can help optimize energy use, improve reliability, and reduce costs. Implement a comprehensive energy management plan to reduce energy consumption and lower operating costs. This may include measures such as installing energy-efficient lighting, optimizing equipment operation, and educating employees about energy conservation. Periodically review the electrical system design to ensure that it meets the current needs of the pump house. As loads change over time, the system may need to be upgraded or modified to maintain reliable operation. If the pump house is located in an area with a high risk of lightning strikes, consider installing a lightning protection system. Lightning strikes can damage or destroy electrical equipment and can also cause fires. Properly train all personnel who operate or maintain the electrical system. This can help prevent accidents and ensure that equipment is operated safely and efficiently. When working on electrical equipment, always follow proper safety procedures. This includes wearing appropriate personal protective equipment, such as gloves and eye protection, and using insulated tools. Before working on any electrical circuit, always verify that it is de-energized. Use a voltage tester to confirm that the circuit is not live. Never work on electrical equipment while standing in water or on a wet surface. Water is a conductor of electricity and can increase the risk of electric shock. If you are not qualified to work on electrical equipment, hire a qualified electrician. Working on electrical equipment can be dangerous and should only be done by those who are properly trained and equipped. Always follow the manufacturer's instructions when installing or maintaining electrical equipment. Improper installation or maintenance can damage equipment and can also create a safety hazard. Consider the use of arc flash protection to protect workers from the hazards of arc flash. Arc flash is a dangerous electrical explosion that can cause serious burns and other injuries. Implement a lockout-tagout program to prevent accidental energization of electrical equipment during maintenance or repair. Lockout-tagout procedures ensure that the equipment is properly de-energized and that it cannot be accidentally turned on while work is being performed. Regularly test ground fault circuit interrupters, or GFCIs, to ensure that they are working properly. GFCIs are designed to protect people from electric shock by interrupting the circuit when a ground fault is detected. Install smoke detectors and carbon monoxide detectors in the pump house to provide early warning of fires or carbon monoxide leaks. Test the detectors regularly to ensure that they are working properly. Keep the pump house clean and free of clutter. Clutter can create a fire hazard and can also make it difficult to access equipment in an emergency. Store flammable materials in approved containers and in a well-ventilated area. Flammable material should be stored away from heat sources and ignition sources. Develop an emergency plan to address potential electrical hazards such as fires, floods, and power outages. The emergency plan should include procedures for evacuating the building, shutting off power, and contacting emergency services. Periodically review and update the emergency plan to ensure that it is current and effective. Conduct regular safety audits to identify potential electrical hazards and to ensure that safety procedures are being followed. Correct any hazards that are identified during the safety audits. Encourage employees to report any electrical hazards or safety concerns to management. Promptly investigate and address any reported concerns. Promote a culture of safety in the workplace. A strong safety culture can help prevent accidents and injuries. By carefully considering these factors and implementing appropriate measures, you can ensure that the electrical system in the pump house is safe, reliable, and efficient. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations. Familiarize yourself with the NEC requirements that apply to the pump house and ensure that all electrical work complies with these requirements. Local electrical codes may also have additional requirements that must be followed. Contact the local electrical inspector to determine the specific requirements that apply to the pump house. When selecting electrical equipment, choose products that are listed by a recognized testing laboratory, such as Underwriters Laboratories or all. Listed products have been tested and certified to meet safety standards. Use only approved wiring methods for the specific application. The NEC specifies the types of wiring methods that are permitted for different applications. Ensure that all wiring is properly supported and protected from physical damage. Wiring should be supported by clamps, straps, or other approved means. Avoid running wiring through areas where it could be damaged by vehicles or equipment. Use conduit to protect wiring in exposed or hazardous locations. Conduit provides a physical barrier that protects wiring from damage. Properly sized conductors to carry the intended load. The NEC specifies the minimum conductor size for different opacities. Use overcurrent protection devices such as circuit breakers and fuses to protect wiring from overloads and short circuits. Overcurrent protection devices should be sized to protect the wiring and equipment they serve. Ground all non-current carrying metal parts of electrical equipment. Grounding provides a path for fault current to flow back to the source, which helps to prevent electric shock. Use ground fault circuit interrupters, or GFCIs, in wet locations such as bathrooms and kitchens. GFCIs are designed to protect people from electric shock by interrupting the circuit when a ground fault is detected. Install surge protection devices to protect sensitive electronic equipment from voltage surges. Surge protection devices should be installed at the service entrance and at individual equipment locations. Use arc fault circuit interrupters, or RFCIs, in bedrooms and other areas where there is a high risk of arc faults. RFCIs are designed to protect against fires caused by arc faults. Properly label all electrical equipment and wiring. Labeling helps to identify the purpose of the equipment and wiring, which can prevent accidents and make troubleshooting easier. Keep electrical panels and equipment accessible. Do not block access to electrical panels or equipment with storage or other items. Regularly inspect electrical equipment and wiring for signs of damage or wear. Replace any damaged or worn equipment or wiring immediately. Repair any electrical hazards that are identified during inspections. Do not ignore electrical hazards, as they can lead to accidents and injuries. Follow all safety procedures when working on electrical equipment. Electrical work can be dangerous and should only be done by qualified personnel. Always de-energize circuits before working on them. Use a voltage tester to verify that the circuit is de-energized before starting work. Wear appropriate personal protective equipment, such as gloves and eye protection, when working on electrical equipment. Use insulated tools when working on electrical equipment. Never work on electrical equipment while standing in water or on a wet surface. Water is a conductor of electricity and can increase the risk of electric shock. Be aware of the potential for arc flash. Arc flash is a dangerous electrical explosion that can cause serious burns and other injuries. Use appropriate arc flash protection when working on energized electrical equipment. Follow all lockout-tagout procedures to prevent accidental energization of electrical equipment during maintenance or repair. Lockout-tagout procedures ensure that the equipment is properly energized and that it cannot be accidentally turned on while work is being performed. Develop an emergency plan to address potential electrical hazards, such as fires, floods, and power outages. The emergency plan should include procedures for evacuating the building, shutting off power, and contacting emergency services. Periodically review and update the emergency plan to ensure that it is current and effective. Conduct regular safety audits to identify potential electrical hazards and to ensure that safety procedures are being followed. Correct any hazards that are identified during the safety audits. Encourage employees to report any electrical hazards or safety concerns to management. Promptly investigate and address any reported concerns. Promote a culture of safety in the workplace. A strong safety culture can help prevent accidents and injuries. The recommendation to pull off one leg of the 480-volt service and use a single-phase transformer to step down to 120/240 volts is contingent on several factors. The primary advantage is isolating the single-phase loads and preventing them from directly affecting the three-phase balance. However, this creates a significant unbalance on the 480-volt side. The degree of unbalance depends on the size of the single-phase transformer relative to the overall three-phase load. It is essential to calculate the current drawn from each of the three 480 volts phases with the single-phase transformer operating at its maximum load. The resulting phase current should be compared to the ampacity of the conductors and the capacity of the upstream equipment, such as the service disconnect and any transformers. The NEC addresses unbalanced loads in several sections. Table 310.15. Beat 3. It provides adjustment factors for ampacity of conductors and raceways or cables with more than 3 current carrying conductors. If the neutral conductor carries a substantial portion of the load current, it may need to be counted as a current carrying conductor. Section 220.42 allows for demand factors to be applied to feeder and service load calculations. These demand factors recognize that not all loads will operate at their maximum capacity simultaneously. Section 215.3 requires that feeders be sized to carry a calculated load. Section 230.42 provides similar requirements for service conductors. In addition to the NEC requirements, utility companies may have their own requirements for unbalanced loads. These requirements may be more stringent than the NEC requirements. Contact the local utility company to determine their specific requirements. Before implementing the single-phase transformer solution, consider the following. Firstly, perform a thorough load analysis to determine the actual demand of the 120 volts and 240 volts loads. Secondly, calculate the resulting phase currents on the 480 volt service with the single-phase transformer operating at its maximum load. Thirdly, compare the calculated phase currents to the ampacity of the conductors and the capacity of the upstream equipment. Fourthly, verify that the resulting unbalance does not exceed the NEC requirements or the utility company requirements. Fifthly, consider the impact on voltage regulation. A large single-phase load can cause voltage drop in the 480 volt service. Sixthly, implement appropriate measures to mitigate any potential problems, such as increasing the size of the conductors or using a voltage regulator. Alternatively, if the unbalance is deemed unacceptable, consider other options, such as using a three-phase transformer with a zigzag or delta Y connection to supply the 120/240 volts loads. These transformers are designed to mitigate the effects of unbalanced loads. Another option is to distribute the 120 volts and 240 volts loads more evenly across the three phases. This may require reconfiguring the electrical circuits or using additional transformers. If the 240 volts loads are critical, consider using a separate three-phase transformer to supply these loads. This will isolate the 240 volts loads from the 120 volts loads and prevent them from affecting the three-phase balance. Finally, always consult with a qualified electrical engineer to determine the best solution for the specific application. An electrical engineer can perform a thorough load analysis and recommend the most appropriate equipment and wiring methods.